So welcome. Now we are starting with section 8 of API 577 recommended practice. The section 8 is going to be non-destructive testing. Before the video previous to this, we have already seen that what is section 5, section 6 and section 7. Section 5 was welding material, section 7 was WPS and PQR, and section 6 was WPS and PQR, and section 7 was welder performance qualification. Now we are coming in to the heart of this document, which is going to be the non-destructive examination. The non-destructive examination that an inspector would recommend or would do to identify various kinds of welding discontinuities in a weldment, specifically if it's a repair, alteration or a newer fabrication. So we already know that there are multiple non-destructive examination test techniques that a person can perform on a weldment. So you can have penetrant examinations, you can have magnetic particle examination. For volumetric, you can do radiography, ultrasonics. You can also go for eddy current examination, which is generally not recommended for weldings, but still it can be done. Okay. So discontinuities and imperfection, the non-destructive examination is defined as those inspection method that allow the material to be examined without changing or destroying their future usefulness. The non-destructive examination is an integral part of organization's quality assurance program. Several non-destructive examination methods are employed to ensure that the weld meets the design specification and does not contain any kinds of defects. The inspector should choose the non-destructive method based on the capability and adequate sensitivity to detect discontinuities in the weld joints, requiring the examination for accept and reject evaluations. Table 2 and figure 13 list the common types and location of the discontinuity illustrated in the position within the butt weld. The non-destructive method most commonly used during the weld inspections are shown in table 3. Table 4 lists the various joint types and common non-destructive method able to inspect their configuration. Table 5 lists down the detection capabilities of most non-destructive examination methods. The inspector should be aware of the discontinuities and that are common to the specific base metals and weld processes to ensure that these discontinuities are detectable. Table 6 is the summary of the discontinuities and potential non-destructive methods and possible solution to the weld process. So this is table 2. This table 2 is telling you that what kind of discontinuities are possible in a weldment. So we already know that there is something known as porosity. Porosity is gas entrapment or air entrapment. Now porosity is generally on a weldment. It can be below the weld, it can be on top of the weld, it can be at any location, but it is generally circular in nature. How you are seeing the porosity or what is the distribution of porosity, based on that there are multiple classifications. So porosity can be uniformly scattered, it can be a clustered porosity, it can be a piping porosity, it can be a linearly aligned porosity. It can also be elongated porosity, sometimes known as piping porosity or a wormhole porosity. The location is going to be the weld metal zone, that is going to be the under weld metal, and the porosity can also be found in the base metal and the heat affected zone if the base metal is casting. Inclusion, so you can have slag inclusion, tungsten inclusion. Generally it is going to be between the weld metal zone and the weld interface. Incomplete fusion can be between the weld metal zone between two passes, or between the weld interface between the base metal and the filler metal. Incomplete penetration, that is lack of penetration, it will be in the base metal zone at the root of the section. Undercut is generally going to be the weld interface or the heat affected zone adjacent to the weld toe or the weld root in the base metal. Underfill, weld metal zone when the weld is not completely filled. Lamination is in the base metal generally near mid thickness of the section. Delamination, base metal zone. Seam lap in the base metal zone, lamellar tear in the base metal zone. Cracks, we already know what is a crack, but depending on how you are able to see that crack, it is further classified into longitudinal crack, transverse crack, crater crack, throat crack, toe crack, face and root crack, and underbead and heat affected zone crack. So longitudinal and transverse crack are more common cracking that you will be seeing on a weldment. So longitudinal and transverse crack can be in the weld metal zone, heat affected zone and the base metal zone. Crater crack would be in the weld metal zone, generally at the start or stop of the weldment. toe crack is going to be in the weld interface and the heat affected zone. Face and root crack is going to be in the weld metal zone, and underbead and heat affected zone cracking will be in the heat affected zone. Concavity, weld metal zone. Convexity, weld metal zone. Weld reinforcement, weld metal zone. Spatter can be anywhere. It can be weld metal zone or base metal, anywhere it can be. Arc strike also can be at any location. So these is a possible distribution of base metal for butt welding. So here you are able to see that what kind of discontinuity and what are some probable location of that discontinuities in a weldment. So these are common types of non-destructive examination that a person or an inspector can recommend for identifying various discontinuity. You can have visual testing, which is generally going to be the initial testing that you are going to perform on a weldment. Magnetic particle examination, wet fluorescent magnetic particle examination, liquid penetrant examination, leak testing, eddy current, radiography, ultrasonic and ACFM, that is alternating current field measurement. These are some capabilities of the weld joints that can be inspected by various non-destructive examination. Here you have to see this, okay? So in butt welding, RT is very good. UT is also very good. PT, MT, UT, RT, anything can be done on a butt weld, but eddy current, PT, MT, VT are only going to be good for surface detection, whereas RT and UT are going to be for volumetric inspection. In corner joints, you cannot do RT. It is marginally applicable, and that means not 100% inspection can be done. But yes, you can do some inspection, but not 100% can be inspected. But UT can be done. Same thing with other testing also. PT, MT can be done on any interface or any product form, provided that the defect is on the surface or subsurface. T joint, again RT would not be done, but UT can be done. Lap joint, RT cannot be done, UT can be done. Edge joint, UT also marginally applicable, RT is also marginally applicable, but other testing, that is surface detection technique, most of the surface detection technique, that is PT, MT, PT, MT, VT can be done on most of the interfaces, provided that a defect is on the surface. So these are some kinds of discontinuity that can be detected by some kind of non-destructive examination. So discontinuity that has very good volume can be easily identified by radiography. So porosity can be easily identified by radiography. Slag inclusion can be easily identified by radiography. Incomplete fusion, it can be marginally applicable because lack of sidewall fusion can be seen. It can be understood as well. But lack of interpass fusion would be really difficult to detect, because interpreter might get confused that whatever he's looking, is it a lack of interpass fusion, a longitudinal crack or something else. Okay. Incomplete penetration, obviously RT can be one of the better choices for this. Undercut, RT can show you better. Overlap cannot be seen by RT. Crack, marginally applicable. If you have good orientation of crack, that it can be detected, but if it's not good orientation, crack would not be detected. Lamination again cannot be detected by radiography. But same thing with UT. In UT, volumetric discontinuities can be seen, but you cannot identify what kind of discontinuity it is. That is, in UT you can see porosity, you can see a signal for porosity, but you will not be able to exactly call is it the porosity or not. There is some interpretation involved there. So you might get confused between slag inclusion and porosity, because both are going to generally create a signal. Okay, but incomplete fusion and lack of penetration can be easily seen. Undercut and overlap cannot be seen. Crack and lamination are most easily seen. Okay, same thing with PT, MT, VT, eddy current and leak testing. PT, MT, PT is only good for surface, MT is also good for some subsurface, VT is also only good for surface, eddy current is surface and subsurface, and LT is generally going to be for identifying if there is a leak present in a system or not. So generally these 5 methods are going to be selected for any weld inspection. ET and LT are generally not preferred, but again it can be used depending on the circumstances. These are some of the discontinuities that are encountered in the welding process. So hydrogen cracking can be seen in SMAW, flux core arc welding and SAW welds. Typical NDT method is going to be VT, PT, MT. After cool down, the practical solution is use a low hydrogen electrode, preheat and post-weld heat treat the joint. Lack of fusion, all welding processes are subjected to lack of fusion. Typical method of identifying it is going to be UT. The general cause is going to be improper heat input and improper welding technique. Lack of penetration can be in all welding processes. UT, RT, VT are going to be the better testing methods to identify this. Improper heat input and improper joint design are going to be the much more the bigger culprit for lack of penetration. Undercut, SMAW, SAW, flux core arc welding, GMAW. VT is going to be the better option because it is always going to be on the surface. Reduce the current and travel speed. Slag inclusion, SMAW, flux core arc welding, SAW, UT, RT is going to be the better technique. Improper cleaning is going to be the bigger problem. Excessive weaving and improper welding technique are also going to be contributing towards slag inclusion. All of these are for carbon steel. Porosity, all welds would have porosity, so, or at least all welds are subjected to porosity. RT is going to be the better option. Generally use a low hydrogen, low sulfur environment and proper cleaning method and proper shielding also. Burn through, SAW, that is submerged arc welding, flux core arc welding, GMAW and SMAW, VT and RT is going to be the better option, and improper heat input is going to be the culprit for this. Arc strike, all can have arc strikes. VT, MT, PT, macro, H, it can be removed by grinding operation. Lack of fusion, lack of sidewall fusion, GMAW short circuiting method, UT is going to be the better option. Tungsten inclusion is only going to be possible in TIG weldings or GTAW, and RT is going to be the better option. In stainless steel welds, you can have solidification cracking, hot cracking, incomplete penetration, undercut, slag inclusion, porosity, arc strike, tungsten inclusion. Solidification cracking can be identified by PT because it is generally going to be on the surface. Hot cracking, RT, PT, UT can be used. Incomplete penetration, RT and UT are better options. Undercut, VT is the better option. Slag inclusion, RT and UT is the better option. Porosity, RT is better option. Slag, arc strike, VT, PT and macro etching can be a better option, and in tungsten inclusion, RT is going to be the better option. Next is material identification. Obviously, whenever you are using any kind of a material, so we have already discussed what is a P number, what is an F number, but whatever is written, or let's imagine I am buying a base metal with a P number 10, okay? Let's imagine the material is going to be S238. Okay, so I need to make sure that whatever constituents of the S238 steel is, it should be present there. That means I need to understand that is the carbon content as appropriate or not, is the sulfur content appropriate or not, is the manganese content appropriate or not, if chromium content is appropriate or not. So all of these things are to be tested first. Even if material identification, even if the material test certificate is available, still we have to identify that whatever is written in the material test certificate, is it actually corresponding to the metal that we are receiving. For that, we would generally do positive material identification. This is covered in API 578. So during weld inspection, the inspector should verify the conformance of the base metal and the filler metal chemistries for selecting or specified alloyed materials as required by the relevant WPS. This should include the reviewing mill test report, reviewing stamps, markings on the component, or require a positive material identification testing. It is the responsibility of the owner user to establish a written material verification program indicating the extent and the type of PEMI that is outlined by API 578. So we have seen that in most cases visual examination is going to be the primary testing method that we are going to apply. The reason being is that visual testing is much easier to perform. Visual testing, you do not require any special equipment, you just require some gauges and an experienced inspector, and the visual testing can be done. Obviously, we'll talk about all of these entity testings greater when we talk about ASME section 5, but still some ideas given here. So VT is most extensively used non-destructive examination methods for weld. It includes direct or indirect observation exposed to the surface of the weldment and the base metal. The direct VT is conducted when access is sufficient to place the eye within 6 inches to 24 inches of the surface to be examined, and the angle is not less than 30 degrees as illustrated in figure 14. So direct examination is when the part is completely accessible to the inspector. If the inspector can go up from 6 inches to 24 inches between the part and the angle is 30 degrees, then it is going to be the better inspection. Obviously, to enhance the vision, some other things can also be used. But if the area is not accessible to the inspector, then you can use some specialized equipment that will help you to see things clearly. These are known as visual aids. So you can use boroscope, you can use CCTVs, you can use robotic crawlers to go to the area where it is not accessible for the inspector to go, but you can take an image out of it and you can see that image on any kind of a screen. So remote VT may be substituted for direct examination. Remote examination may use aids such as telescope, boroscope, fiber boroscopes, cameras or other suitable instruments, provided they have a resolution at least equivalent to those obtained during direct examination. So you can do remote examination provided that whatever results that you are getting from the direct examination, from the indirect examination or remote examination, is comparable to what you were getting during direct examination. ASME Section 5 Article 9 lists the requirement for visual testing. Codes and specification may list the compliance with these requirements as mandatory. Some requirements are listed below. So these are the requirements. Obviously we'll talk about these requirements greater when we talk about ASME Section 5, but here are the lists that are written. These are the requirements for visual testing procedure. So you have to have a written and a qualified procedure. The minimum amount of information that is to be included in the written procedure. Demonstrate the adequacy of the inspection procedure. The inspection personnel must be certified. The inspection personnel are required to have eye test, and the vision should be, near vision should be at least comparable to J1 vision. Direct VT requires access to permit the eye to be within 6 inches to 24 inches, and the angle should not be less than 30 degrees. The minimum required illumination for the part of examination, generally now the illumination for as per the ASME Section 5 is going to be 100 feet candles or 1076 lux. The indirect VT permits the use of remote examination and devices employed, evaluation of indications in terms of acceptance standards and referencing code, and a form of adequately documenting the results as per the relevant code. Visual testing tools. Now, visual testing is much easier to do because you just need an inspector and you just need the inspector to see the part and the assessment can be done. But if you want to see things clearly, if the area is not accessible, if you want to go to the area that is not accessible, or if you want to magnify the image, in that case some visual aids are required or tools are required. So there can be n number of tools. Obviously these tools might be something like a mirror or a magnifying glass or a boroscope, but these will not help you to take any measurements. For measurements you require some mechanical aids such as vernier caliper, micrometer, different types of welding gauges can be used. So these are all the tools that are going to assist the visual inspector to see things clearly basically. So there are different types of visual inspection tools to inspect and evaluate the weldments. The adequate illumination and a good eyesight are the basic requirements. In addition, a basic set of optical aids and measuring tools specifically designed for weld inspection can assist the inspector. In following subsections are more commonly used tools and methods for visual testing of welds. Optical aids are used in visual inspection includes following. Lighting requirement as per ASME Section 5 Article 9 is going to be 100 feet candles or 1076 lux. Mirrors can be used, magnifying glasses can be used, and boroscopes and fiber boroscopes can be used. Mechanical aids would be something that will help you to take measurements. So you can use a steel rule, a vernier caliper, combination set square set, mechanical thickness gauges, and various kinds of levels. Weld examination devices, so you can have various kinds of weld inspection gauges. You can have fillet gauges, palm green gauges, bridge cam or cambridge gauges. You can use a high-low gauges. Different type of gauges can be used to inspect the weldments. So you can have inspector's kit. Inspector kit is, the figure is given below. The bridge cam gauge can be used. Fillet weld gauges can be used, which is only good for identifying billet welds or T-joints. You can use weld size gauges, you can use high-low gauges. High-low gauges are generally used for identifying mismatches. Digital or infrared pyrometer or temperature sensitivity crayons can also be used. So this is a kit for the visual inspector. So a visual inspector would generally be using this to identify the weldments. This is a bridge cam gauge. So this kind of gauge is going to be much better for all kinds of inspection because this can identify multiple things. This can tell you about bevel angle. So in this case, this is telling you the bevel angle of this joint. Okay. It can also tell you about the pit depth. It can also tell you about undercut depth. It can also tell you about how much weld reinforcement is present. It can also tell you if there is mismatch between two plates. It can also tell you the throat size. It can also tell you leg lengths. All of these things can be done by bridge cam gauge. So if you have this gauge, most of the weld gauge equipments are generally going to be eliminated, because this is basically weld gauge on steroids. Okay. So this is a adjustable fillet gauge. This is a skew T fillet gauges, generally used for TKY joints. This is a fillet weld gauge, generally only going to be used for fillet welds, that is T joints. This is also a fillet weld gauge. This is a palm green gauge, also known as weld size gauge. This can tell you about the throat size of the fillet weld, and it can also tell you about weld reinforcements. This is a high-low gauge, generally used for identifying mismatches between two matching interfaces. The next kind of examination that a person can do is going to be magnetic particle examination. So magnetic particle examination is generally used for identifying surface as well as subsurface discontinuities. This can only be done on a ferromagnetic material. It cannot be done if the material is not ferromagnetic. So MT is an effective way in locating surface and near surface discontinuities in ferromagnetic material. It is most commonly used to evaluate weld joint surfaces, intermediate checks for weld layers, back gouge surfaces for completed welds. Typical types of discontinuity that can be detected using MT with adequate accessibility includes crack, lamination, laps, and seams. In this method, the weld and the heat affected zone is locally magnetized, so you will have something that will magnetize it, especially in the site. We generally use a yoke to magnetize the part, creating a magnetic field in the material. Finely divided ferromagnetic particles are then applied to the magnetized surface. The draws bakes, okay, something like this. So first, the thing is, if I want to check this area, we would first clean it. While cleaning, the aim is that the part should be clean and dry. Then we'll have a yoke. Yoke will generally be an electromagnet that has two legs. One is going to behave like a north pole, other is going to behave like a south pole. So you'll magnetize this local area, and if there is any discontinuity, there would be a change in magnetic field. So this change in magnetic field, or the disruption in the magnetic field, can be seen by spraying iron powders on it or iron particles on it. These iron particles will be attracted to not only at the poles of the yoke, but also at the areas where the magnetic disruption is happening or the flux leakage is happening, and this will help you to identify where the discontinuity is. In this method, the weld and the heat affected zone is magnetized, creating the magnetic field in the material. Finely divided ferromagnetic particles are then applied to the magnetizing surface and are drawn to break in the magnetic fields, resulting in the discontinuity. The particles used in the examination can either be wet particles or dry particles. So dry particles is basically powder. Wet particles are powder that are suspended in some kind of a liquid. Depending on the type of imperfection or the examination and the level of sensitivity is required. So wet particle is generally more sensitive. Dry particle is not as sensitive because dry particles has no capability of moving once it is on the surface. But dry particle is generally going to be much better for identifying subsurface discontinuity, whereas wet particles are going to be much better for identifying surface cracks or surface defects. If the examination is performed in the normal lighting, the color of the particles are going to be providing a better contrast between the surrounding background. So if you are viewing the particles under normal light, it is considered to be visible testing. If you are viewing the particles under a special kind of UV light, then it is generally considered to be a fluorescent method. The best results are achieved when the lines of flux are perpendicular to discontinuity. So discontinuity and the magnetic flux should be 90 degrees from each other, or 45 to 90 degrees, because if the orientation of the defect is less than 45 degrees from the flux direction, then it is not going to show up as an indication. The inspection should overlap by at least 2 inches. The two inspections are typically performed, one parallel and one perpendicular to the weld, providing maximum probability of coverage. So once it will be like this, and other time it would be like this. Okay, so 90-degree coverage. So any surface that is going to be examined by magnetic particle testing has to be done 2 times. Okay. When the magnetic force is applied to the material, the flux is created. Flux field is created around and through the magnet through the material. The discontinuity that is perpendicular to the lines attract the magnetic particle, causes an indication to show up. For added sensitivity, wet fluorescent magnetic particle testing may be used with a black light. ASME Section 5 Article 7 will list the requirements for MT. Some codes and specification may list the compliance with these requirements as being mandatory. ASME B31.3 and ASME Section 8 Division 1 requires MT to be performed in accordance with Article 7. So we'll talk about this when we go to section 5, but here are some requirements listed below. So examination procedure information, use of continuous particle and application method, use of one of the 5 magnetizing techniques. There are 5 magnetizing techniques. You can have longitudinal magnetization, you can have circular magnetization, you can have prod magnetization, you can have yoke magnetization, you can have multi-directional magnetization, you can have central conductor magnetization. So different kinds of magnetizing techniques can be used. The required calibration of the equipment, 2 examination perpendicular to each other, maximum surface temperature for the examination, magnetizing current, evaluation of the indication in terms of acceptance standards of the referencing book, the demagnetization, and minimum required surface illumination, that is visible light requirements and black light requirements. Flux direction indicator, so you can have different kinds of indicators to tell you that what kind is the direction of the flux that has been generated. Generally there are different kinds of shims or pi gauges that can be used. So direction of the magnetic flux can be confirmed by use of several indicators. One of the most popular indicator is a pi gauge. Pi gauge consists of 8 pieces or 8 low carbon steel segments braced together in an octagonal shape. This bracing is done with copper. So copper will not generate its own magnetic field. So whichever line doesn't show up during the testing, that would be the direction of magnetic field. So this is a yoke. The center section is the weldment. One will act as a north pole, other will act as a south pole, and this entire area would get magnetized. Something like this. So once it is like this, and the next time it will be perpendicular, this would be the next shot. Something like this. So once it's like this, the second times it's like this. So all possible discontinuities which are greater than 45 degrees in both orientation would be detected. This is a pi gauge. This will tell you about the direction of magnetic field. The final thing we have to do is demagnetization. When the residual magnetic field in the part could interfere with subsequent processing or usage, the demagnetization technique should be used to reduce the residual magnetic field to within the permissible limit. The care should be taken when performing MT during the welding process. If the residual magnetic field is left in the partially completed weldment, this may deflect the magnetic arc. This is known as arc blow, and it could make it difficult to control the weld deposit. The next technique that we can use, next method that we can use is ACFM. Not widely used, but again, it is a possibility that it can be used. So ACFM is a sub-technique of electromagnetic method. It is a non-contacted technique that is able to detect and size surface breaking imperfection in a range of different materials and through coating of various thicknesses. This technique can be used for inspecting complex geometry such as nozzle, ring grooves, and grind out areas. It requires minimal surface preparation and can be used at elevated temperatures about and up to 480 degrees Celsius. However, it is less sensitive and more prone to operator errors than wet fluorescent magnetic particle testing. ACFM is used for evaluation and monitoring of existing cracks. ACFM uses a probe similar to eddy current probe and introduces an alternating current in a thin skin near the surface of any conductor. If there is any change in this alternating current that is provided by the probe, this can be detected by ACFM. During the application of ACFM technique, the actual values of the magnetic field are being measured in real time. These are used in mathematical model lookup tables to eliminate the need for calibration of ACFM instrument using the calibration piece with artificial defects such as slots. The next widely utilized method is going to be liquid penetrant examination. I hope you guys have all seen what is liquid penetrant examination. If not, I'll make a different video series where I'll be showing all of these testing. So in penetrant testing, generally the penetrant testing is going to be the most easiest testing that a inspector can perform on a weldment. But this technique will not show you any defect that is subsurface. It can only tell you a defect that is open to the surface. Okay. So PT is capable of detecting surface connected discontinuities in a ferrous and a non-ferrous material as well as non-metal objects. So MT was not good for non-ferromagnetic material or non-ferrous objects, but PT can tell you about non-ferrous objects also. PT can be used to examine in weld joint surfaces, completed welds, and perform intermediate checks of individual weld passes. This technique is commonly employed on austenitic stainless steel where MT is not possible. The examiner should recognize that there are many specification limits limit containments in the penetrant material that could adversely affect the weld or parent materials. Most penetrant manufacturers provide material certification on the amounts of contaminants such as chlorine, fluorine, sulfur, halogens, etc. Next thing is capillary action. Capillary action is rise or fall of liquid in thin sections, or basically due to capillary action the liquid will force to go inside wherever the opening is. So the penetrant liquid is going to be something that is capable of doing capillary action. So capillary action is the basis of the penetrant to be drawn inside the material. The reverse capillary action is a principle that is behind the visualization of the indication after the application of developer. The limitation of PT is that the standard penetrant system is restricted to a maximum temperature of 52 degrees Celsius. So weld or material to be inspected must be below this temperature, which significantly slows down the welding operation. Additionally, this method requires extensive cleanup so as not to contaminate the weld surface. High temperature penetrant system can be qualified to an extent the temperature envelope. So you can have high temperature penetrants also, but general penetrant system is only going to be good for 5 degrees to 52 degrees Celsius. Penetrant technique. Two kinds of technique can be used. Again, a visible and a fluorescent method. So in a visible method, the penetrant indication can be seen under a visible light or a white light. In fluorescent testing, the penetrant is going to be shining under a UV light. So the inspection is going to happen under a UV light, which will increase the sensitivity of a system. So two general penetrant technique approved for use of color contrast penetrant technique and a fluorescent penetrant technique, which uses a fluorescent dye that is visible using an ultraviolet light. So it looks something like this. So this is a linear indication, a crack that can be seen on a weldment. There are different kinds of penetrant systems that are available: solvent removal, water washable, and post emulsifier technique. Most cases solvent removal is used, but the possibility is there that if you have rough welds or welds in a large quantity, then you can use water washable system also. If the area is not accessible, then you can use a post emulsifier testing also. If this post emulsifier generally also has a better sensitivity, water washable have the lowest sensitivity, and solvent removal will have generally higher sensitivity. ASME section 5 article 6 will tell you about the requirements of penetrant testing. API 650, ASME B31.3, ASME section 8 division 1 require PT to be performed in accordance with ASME section 5 article 6. Some requirements that are to be followed are listed below. So these are the requirements that are to be followed while doing or while performing penetrant examination. The inspection is to be performed in accordance with the procedure. Type of the penetrant material to be used, details of pre-examination cleaning including minimum drying time, dwell time for the penetrant, details for removing excess penetrant, applying the developer, and time before interpretation, evaluation of the indication in terms of acceptance standards from the referencing book, post-examination cleaning requirements, and minimum required surface illumination for viewing the indication. Next is eddy current examination. Eddy current examination is not widely used for weldments because generally in the weld you will have different conductivity around the heat affected zone because of the heat applied, but again it can be used depending on the configuration we are talking about. So eddy current inspection is used to detect surface imperfection, in some cases subsurface discontinuity, in a tubing, pipe, wire, rod, bar stock. ET has a limited use in weld inspection. ET can be used in a quick test to determine the components being joined during the welding have same properties. And as a quick check for imperfection of the weld joint surfaces, it can also be used to measure thickness of the protective and non-conductive surface coating and cladding thickness. Again, while using this, you can use section 5 article 8 which addresses electromagnetic testing or eddy current testing of tubular products. Tangential eddy current examination. Tangential eddy current examination introduces alternating currents into the surface, into the tested component, and detect and size surface breaking cracks. This method uses a probe to introduce the current and alert the operator for the presence of any kind of defects or discontinuities and their magnitude. The method used for a multiplex tangential coil, pancake coil allow the scan of wide surfaces in a single pass to reduce inspection time. Okay, so these are surface detection techniques. Now we'll go for volumetric examination. Volumetric examination are generally going to be radiography and ultrasonic examination. So RT is a volumetric examination capable of examining the entire specimen rather than just the surface. So it can tell you about external and internal defects also. In is the historical approach to examine the completed wells for surface and subsurface discontinuity. The method uses the change in absorption of radiation by solid metal and the areas of discontinuities. The transmitted radiation causes the permanent change of the well to be captured on a film. The alternate method can be used to create image in computed radiography or digital radiography. These are some newer techniques of radiography. Initially it was film radiography. Nowadays we can have computed radiography and digital radiography. Any of the methods will create a negative image of the material being examined, as thicker section will appear lighter and thinner section will appear darker. The areas with higher density will appear brighter and areas with lower density will appear darker. Due to the hazard of radiation and the licensing requirement, the cost of RT can be higher and the trained and the certified personnel less available than other NDT methods. NDT examiner who performs film interpretation, evaluation and reporting shall be certified minimum to an ASNT level 2 requirements. However, all personnel performing radiography are required to attend radiation safety training and comply with applicable regulatory requirements. ASME Section 5 Article 2 provides the general requirements for radiography. So these requirements include method to determine if the backscatter is present, permanent identification traceable to the component, film selection in accordance with SE 1815, designation for hole and wire type quality indicators, suggested radiographic techniques, facility to view radiograph and calibration of radiographs. The creation of radiograph is considered acceptable when it meets the required quality features in general terms of sensitivity and density. These factors are designed to ensure that the imperfection of a dimension relative to the thickness of the metal, relative thickness is revealed. Quality indicators. So while performing the radiograph, the main important thing that we are receiving out of it is image. If you receive a good image, if you receive an image that is as per the specification, then an interpretation can be made. But if the image that you are getting, if the image is not as per the specification, or if the image is not clear enough, then you cannot make anything out of it. So to identify what is the quality of the image, we are generally going to use some tools that will help us to assess the quality of the image. These tools are known as image quality indicators. Sometimes they are also known as pentameters. There are various types of it, but as per the requirements of ASME Section 5, there are generally two standard types of it, a hole type IQI and a wire type IQI. So standards for industrial radiography require the use of one or more IQIs, that is image quality indicators, to determine that that the required sensitivity has been achieved. IQI was previously called a pentameter, but the term is no longer used in most codes. To determine the radiographic sensitivity, require a plaque type or a hole type IQI or a wire type IQI, specified by the governing code, and must be clearly visible on the radiograph. Mistakes with IQI selection can have much greater impact on the interpretation of the radiograph of the thinner wall pipe, where large root passes imperfection can significantly reduce the strength and integrity of the weld. IQI are tools used in industrial radiography to establish the quality level of the radiographic technique, but are not used to determine the size of the imperfection. So IQI is just telling you about the image quality, it will not be helping you to identify the size of the discontinuity. IQI are selected on the following basis. The material to be radiographed, IQI should be made up of same material as your base metal, or it should have the same absorption and transmission coefficient for radiation as your base metal. Thickness of the base metal plus the weld reinforcement will also have a say in what kind of IQI you are selecting. There is an entire table given in ASME Section 5 which will help us to identify that at what thickness what number of IQI is needed. There are two general types of IQI. You can have a hole type IQI and a wire type IQI. The wire type IQI are constructed with an array of 6 parallel wires of specified diameter encased in plastic. They are made of a material that is radiographically similar to the component being radiographed. Wire type IQI is placed on and perpendicular to the weld prior to the exposure of the radiograph. The diameter of the essential wire based upon the code requirements as the function of thickness. Visible as lighter image on the radiograph, the documents that radiographic technique is required sensitivity and as the function of contrast and definition. Hole type IQI. Hole type IQI are plaques of known thickness with holes of specified diameter drilled or punched through the sheet. They are made of a material that is radiographically similar to the material being radiographed. The thickness of the IQI is specified by to represent approximately 2% or 4% of the thickness of the object to be radiographed. The holes in the IQI are projected on the radiograph as darker areas. the ability to see the plaque outline and the diameter of the required holes visible in the darker image document the sensitivity of the radiograph technique. The diameter of the hole type IQI are multiple thicknesses of the sheet. The hole type IQI are placed adjacent to the weld either on the parent metal or on a shim having the thickness equivalent to the weld combined the reinforcement of the metal. So this is the table that is given. We'll talk about this table later on when we go at ASME section 5, but this is what essentially a hole type IQI looks like. So you have a smaller hole that is known as 1T, a slightly bigger hole that is known as 2T, which is twice of 1T, and 4T, which is 4 times of 1T. Okay, so this is placed next to the next to the weldment. So when interpreting the weldment, first thing we'll look at is going to be the image of the IQI. If everything in the IQI is visible, then you can go ahead in interpreting the radiograph, because this will prove that your image is of a better quality and you are at least able to see everything. Okay, it's something like this. So this is a 1T hole, this is a 2T hole, and this is a 4T hole. Next is radiation source selection. So for weld inspection, iridium 192, cobalt 60, selenium 75 radioactive isotopes are used. X-ray machines may also be used. Iridium 192 is normally used for performing radiograph on steel with the thickness ranges of 0.25 to 3 inches. Cobalt 60 is used for steel thicknesses that is generally greater in sizes. It is going to be between 1.5 inches to 7 inches. The minimum or maximum thickness that can be radiographed for a given material is determined by demonstrating the required radiographic sensitivity has been documented. Radiographic film. Although digital recording of the radiography is sometimes used, the radiographic film class 1 or class 2 is extensively used for industrial radiography. The film is required to be of a sufficient length and width to allow the minimum of 1 inches or consecutive circumferences exposed, and 3 by 4 inches, that is 19 mm coverage on the either side of the weld. So allow a minimum. So if this is your weld area, 1 inch on either side would be generally radiographed to identify if there is any kind of a defect on the weld area or in the heat affected zone. Film processing. So exposed film can either be manually processed or the examiner may use an automatic processor. Typical development time is going to be 5 to 8 minutes. Surface preparation. The surface condition could mask imperfection. So if visually detected by the radiographer prior to radiography, should be remedied prior to the exposure. Radiographic identification, radiographic techniques. The most effective technique from both quality and effective standpoint is going to be one with the radiography passes through the single thickness of the material being radiographed, and the film is in contact with the surface opposite to the source side. So generally when we are doing a radiograph, the object should be like this. You have source on one side, film on the other side. Okay, and whatever happening in this area would be represented on the film which is on back side. But there are multiple techniques also available. These techniques will generally be used for pipe radiography or circular section radiography. The techniques are going to be single wall technique or double wall technique. In single wall technique, you can have single wall single image. In double wall, you can have double wall single image and double wall double image or elliptical shot. So it's something like this. So this is known as single wall single image or single wall exposure, where you have source on one side, film on the other side. This would also be considered as single wall technique because source is inside and film is outside. This would also be considered as a single wall technique because the source is at the center and the film is encompassing the entire 360 degree or circular section. This is known as panoramic image, but all of these are considered to be single wall techniques. The next thing we are going to talk about is a double wall technique. In a double wall technique, this is generally used for pipe sections where the OD or outer diameter of the pipe is less than 3.5 inches. Here, source is outside the pipe, film is also outside the pipe because there is no space inside the pipe. Okay, so the image is going to be overlapping. So the top section is going to overlap on the bottom section, and then the image is going to be represented on the screen. This is known as an elliptical shot, where the top and the bottom section are not going to get overlapped, but you can get an elliptical image out of it. So to complete the 360 degree section here, you would require generally 3 shots. Here you would generally require 2 shots to complete the 360 degree weld. Evaluation of the radiograph. The final step of the radiographic process is the evaluation of the radiograph. Accurate film interpretation is the most essential step in radiographic process. It requires hours of reviewing and understanding the principle regarding the nature of ionizing radiation, as well as different types of images and conditions associated with industrial radiography. A weld crack is generally tight and not always detectable by radiograph unless its orientation is offset relative to the direction of the radiation. So radiography is not the world's best technique to identify cracks, provided that you are getting a good orientation. So transverse cracks are generally much easily seen rather than longitudinal cracks. For example, the radiographic source that is offset plus minus 5 degrees from the weld has a lower probability of detecting crack where the source is offset 10 degrees from the weld. LOF, that is lack of fusion, is typically narrow and linear. It tends to be straighter than a crack. In many cases, LOF is located at the edge of the bevel and requires two subsequent weld passes, and between two subsequent weld passes. This may change to a degree of difficulty in identifying this condition. Facilities for viewing radiograph. Viewing facilities need to provide a subdued background, that is under a subdued. You don't need a dark condition to view the radiograph, but you require a very low light conditions in viewing the radiograph. So the viewing facilities need to provide a subdued background lighting for intensity sufficient to avoid troublesome reflection and shadows or glare on the radiograph. Low power magnification device from 1.5 times to 3 times magnification may be used in aiding film interpretation and evaluation, but a high magnification also enhances the graininess of the film. For example, comparators with scales etched into the glass are often enhanced magnification and measuring capabilities. Quality of radiograph. Radiograph should be free of mechanical, chemical and other blemishes to extent that they do not mask the indication or not confused with the image of any discontinuities in the area of interest. The area of interest in the weld or in the radiograph should be pristine condition. You do not need any kind of non-relevant false indication there, because it will create a confusion. If anything is outside the area of interest, it's not a major concern, but there should be nothing in the area of interest. The radiograph, when blemishes in this area of the interest, shall be discarded and the area shall be radiographed again. We'll talk about this later on when we talk about ASME section 5. ASTM 1316 states the specific portion of the radiograph that needs to be evaluated. This provides a minimum recommended guidance to the inspector while viewing the radiograph. Radiographic density, that is, density is basically color on the radiograph. Okay, the film density is a qualitative measure of film blackening as a result of exposure and processing. Clear film has 0 density value. Exposed film allows 10%. So basically, there are different numbers that are given to density. Okay, so whenever you might have seen an X-ray film, you see that X-ray film is generally black in color. So it's something like this, where different densities are given to the radiograph. So let me show you. So it's something like this. So let's imagine this is your film. Let's imagine if you have 100% light coming from this side, and again 100% light is passing on this side. So it is essentially a transparent section because it's not absorbing anything. So the number of density that is given to this is going to be 0. Again, if the 100% light is coming from this side and only 10% passes, then it is going to be given as 1 number density. Again, 100% of light passes through it and only 1% pass through the film, it is going to be given 2 number of density. Again 100% and 0.1% transmits, it's going to be 3 number density, and again 100% passes and 0.01% transmits, then it is going to be given 4 number density. So this is what density means, and this is what the color means on a radiograph, where 4 number is going to be the darkest color because it absorbs 99.99% of light whichever is coming on the radiograph, where 0 number is going to be the transparent section because it absorbs nothing. Okay. So the exposed film that allows 10% will be given 1 number of density. The film density 2, 3, 4 allows 1, 0.1 and 0.01 respectively to the incident light that passes through. The transmitted image of film density through the radiographic image through the body of hole type IQI or adjacent to the wire type IQI in the area of interest should be within the ranges of 1.8 to 4 for X-rays and 2 to 4 for gamma rays. ASME section 5 tells us that whenever you are shooting a radiograph in the area of interest, you should have minimum 1.8 density if you are doing a radiograph with X-rays and minimum 2 density if you're doing radiograph with gamma rays, and maximum is 4 in both cases. The adequate radiograph density is essential. Rejectable indication conditions in a weld may be undetected if there is a slight density variation in the radiographs are not observed. A densitometer or a step wedge comparison is used to measure or estimate the darkness of the film respectively. A densitometer is an electronic equipment calibrated using a step tablet or a step wedge calibration film traceable to the national standard. A step wedge step wedge comparison film is a step wedge that has been documented to have a specific HND value by the examination by using calibrated densitometer. The density range in the area of interest shall not vary more or less than the specified percentage of the base density as defined in the code or specification. It is a good practice to process an unexposed piece of film daily to determine the pre-exposure conditions of the radiographic film. Next is backscatter radiation. A lead letter B with a minimum dimension of half inch, so half inch height, and 1.5 mm or 1 by 16 inch thickness, letter B is attached to the back of the film. If this B is present, if the darker density of the B on a lighter background will not cause the rejection of radiograph, but if the B image is bright, then the film will be rejected because it will have backscatter and the film is useless. Okay. Interpretation. While doing the interpreter should have these knowledges. So the characteristics of the radiation source and energy levels with respect to the material being examined, characteristics of the recording medium in response to the selected radiation source and energy levels, the processing of the recording medium with respect to image quality, product form, welding process, and geometric configuration of the object being radiographed, possible and most probable types of discontinuity that may occur in the test object, possible variations of the images of the discontinuity as the function of the radiographic geometry and other factors, the acceptance criteria that are to be applied for accept and reject determination. So these are some examples of the discontinuity that you will see. So this discontinuity is lack of penetration. It is going to be represented something like this as a straight line in the center. This is slag inclusion, where you will see irregular shaped dark spots in the entire weldment. This is case of cluster porosity, where you have a porosity accommodated in a single area. This would be the case of lack of fusion, where you are able to see the dot between the weld interface and the base metal interface. This is also lack of fusion. This is burn through. This is mismatch. This is excess penetration. This is root undercut. This is transverse crack. This is tungsten inclusion. This is linearly aligned porosity. So basically these were reference images. So whenever the radiographer might not understand what kind of discontinuity he is seeing, there is some recommendation that is given by the code that will help the radiographer to make a sound decision. Radiographic examination records. These records are to be provided. So these are the minimum points that are written. There are some additional details also that might need to be recorded, but these are the things that are at least required. So job or contract number identification, location marker placement, number of radiograph, X-ray voltage, isotope used, X-ray machine focal spot size, base metal type and thickness, source to object distance, object to film distance, film manufacturer, type and designation, number of films in each holder or cassette, single wall exposure, double wall exposure, single wall viewing, double wall viewing, type of IQI and required hole and wire number designation, procedure or code referencing, the date of examination, name and the qualification levels of the examiners. Ultrasonic examination. So this was radiography, which is most widely used for especially butt welds. We generally don't use radiography examination for other kinds of weld joints, but again, marginally it can still be applicable. So ultrasonic examination. So if you don't do radiography, then you'll generally do ultrasonic, or both can complement each other, because in radiography you are able to see volumetric discontinuity such as slag inclusion, porosity, but you are not able to see crack that easily, or you are not able to see lack of fusion that easily. But that is not true with ultrasonic testing. Ultrasonic testing will show you lack of fusion, cracks, all of those discontinuity, but it will not show you volumetric discontinuity. It will show you the indication, but it will be really hard to pinpoint that what kind of discontinuity it is. It is a porosity or a slag, something like that. So every method will have certain advantages and limitations associated with them. So ultrasonic examination, UT is capable of detecting surface and subsurface or internal discontinuity. The sound beam is an ultrasonic frequency ranging from the frequency level of greater than 20 kilohertz. The travels in a straight line through the metal and reflects from the interface. Straight beam techniques are used for thickness evaluation or check for lamination, another condition which may prevent angle beams from examining the weld. So weld, generally whenever we are inspecting weld, we'll generally be using an angle beam technique. Okay. Shear wave or angle beam techniques are employed for resolution of the discontinuities in a weld. The sound beam enters the area of the weld at a known angle, and this sound is going to reflect from the discontinuity. This reflection of the sound can be detected by an ultrasonic flaw detector machine, and this can tell you that what is the location of the discontinuity, what is the size of the discontinuity, what is the length of the discontinuity, and so on. Type of ultrasonic display, you have A-scan display. So this is known as A-scan display. So whenever the sound enters the material, initially you will see a signal. This signal is known as initial pulse or main bang. Whenever the sound hits the bottom and reflects back, this is known as a back wall signal. And if there is anything in between this, it can be termed as a discontinuity. So this is an A-scan display where you are able to see initial pulse, back wall, and a discontinuity. This is known as a B-scan signal, where B-scan is generally talking about front view of the object. Okay, so when you're looking at the front, you'll be able to see this discontinuity, you'll be able to see the length of the discontinuity, obviously, but you'll not be able to see the depth, you'll not be able to see the width of the discontinuity. You'll not be able to see if it's a circular discontinuity or something like that, but you'll be able to see that there is a discontinuity of this much length in the material. Then in a C-scan, you'll be able to see top view. So in top view, you are able to see what is the shape of the discontinuity, but you are not able to see what is the depth of the discontinuity or what is the location of the discontinuity from the surface. So depending on what kind of inspection you are doing, generally for manual inspection, A-scan is preferred. For automated UT, B-scan is preferred. And for composite material, C-scan is preferred. It depends. Again, you can change it. You can complement each one with other also. So there is a chance that you can do automated UT with B-scan. If you find nothing, then no need of further examination. But when you are doing B-scan, you are able to see a discontinuity. You can supplement it with a manual UT to identify the exact parameters of the discontinuity. All of these things can be done. So B-scan display will be the cross-sectional view, or sometimes understood as a front view of the object. C-scan would be considered as a top view of the object. There is also something known as D-scan. So D-scan shows through thickness view of the cross-section of the test object perpendicular to the scanning surface, perpendicular to the projection of the beam axis on the scanning surface. It's something like this. This is D-scan. You can also have phased array scan, S-scan, but this would generally, as per the requirements of ASME section 8, now this S-scan or phased array can be used in a lieu of radiography, so that can also be done. In S-scan, instead of having one crystal probe, you can have multiple crystal probes that will going to shoot sound at a different rate, so that you can get a picture of the entire section at once. So this entire section at once is known as S-scan or sectoral scan. Okay, it looks something like this. So here you are able to see these discontinuities. It is also paired with A-scan display, so you can get multiple data out of it. Okay. Also, there is a technique known as TOFD, time of flight diffraction. This is one of the best techniques to identify the length of the cracks. So TOFD generally uses a B-scan or a D-scan. Image provides the defect sizing information for through wall extent by using diffracted signals rather than a single pulse echo. In this case, you generally have two probes, one acts as a transmitter, other acts as a receiver, and you get a B-scan data out of it. So this is a B-scan data, and this is a discontinuity signal that you are seeing. Okay, there is a recommendation how to do this inspection is given in ASME section 5, article 4, in one of those mandatory appendixes, but when we'll talk about this later on when we go ahead in ASME section 5. So these are the requirements given for ultrasonic examination in ASME section 5 article 4. These which are the elements required for the written procedure and to be qualified and followed. Some procedure requirements are included here. So weld, base metal types and configuration to be examined. So these are the things that are to be documented while you are doing examination. So weld, base metal types, configuration of the materials to be inspected, technique, couplant type, ultrasonic instrument type, instrument linearity requirements, description of calibration, calibration block material and design, inspection surface preparation, scanning requirements, scanning techniques, evaluation requirement, data to be recorded, reporting of the indication in terms of acceptance regarding to the code section, post-examination cleaning. Now, generally, before you do ultrasonic examination, a calibration is required to understand if your equipment is working as intended. So, ultrasonic examination system calibration is the process of adjusting the control of the ultrasonic instrument, such as UT display of the sound path is linear. Calibration is to ensure that the sufficient sensitivity to detect the discontinuities of the weld and the type expected in the product form and process. So, calibration generally provides you with the reliability that whatever system that you are working with, or whatever settings that you are working with, or whatever conditions you are working with, is it capable of identifying the discontinuity of interest? Because that's why we do calibration. Various kinds of calibration on how to do this is given in ASME section 5. The reference standard. Again, next problem is that ultrasonic testing will not show you what is the size of the discontinuity. Sometimes a reference block is needed to identify the size of the discontinuity. Sometimes a reference block with artificial discontinuity is needed to prove that whatever discontinuity that you need to identify, is it actually capable of identifying that. The reference standard should be of acceptable size and shall have known reflectors. Reflectors is basically artificial discontinuities of specified size and location. These reflectors should be acceptable to the referencing code. So ASME section 5 article 4 will give you some recommendation of how to create these basic calibration blocks. The calibration system checks are required to perform prior to and after the completion of examination. In addition, a system check is required with any change in the search unit is probe, cabling, examiner, and after a specified time frame such as 4 hours. The temperature of the calibration standard should be within 14 degrees of the part being examined. If the temperature falls out of this range, the reference standard should be brought to within 14 degrees Celsius of the object range and the calibration shall be checked. For high temperature work, special high temperature transducers and couplants are necessary. Consideration should be given to the fact that the temperature variation within the wedge or delay line can cause beam angle changes or alter the delay of the time base. System checks are typically performed at a minimum of 4 hours during the process of examination, but they can be done more often at examiner's discretion after any instance of suspected system irregularity. Eco evaluation. So for doing eco evaluation, you can do multiple techniques, but one of the simpler techniques that we generally use is drawing a DAC. So distance amplitude correction curve allows eco evaluation of an unknown reflector by the comparison of the eco height with respect to DAC. Okay. So this is known as a DAC curve. Okay, for drawing this DAC curve, you require a DAC block. We'll talk about this later on when we go to section 5. So basically this line. So let's imagine that this hole is 2 mm. So by plotting these holes at different distances, you'll generally draw this curve, and if anything goes past this, you'll understand it is greater than 2 mm at least. Okay, so this will help your examiner to understand that the size of the discontinuity is above the acceptable level or below the acceptable level without running any calculations. Okay, just makes our life easier. Surface preparation. The surface should be free from well spatter, surface irregularities and foreign matter that might interfere with examination. Examination coverage. The volume of weld, heat affected zone and the portion of adjacent base metal on both sides of the weld should be examined by moving the search unit over the examination surface in order to scan the entire specimen. Each pass of the transducer should overlap with the previous pass by at least 10% of the transducer element dimension. The rate of scan unit movement should not exceed 6 inches per second unless the calibration was verified at an increased speed and the instrument is capable of resolving the imperfection at that speed. In many cases, the search unit is oscillated from side to side to increase the chances of detection of fine cracks that are oriented other than perpendicular to the sound beam. Straight beam examination not generally done for welds, but it can be done for base metal to identify lamination. Angle beam examination, typically there are two different angle beam examination that can be performed on a weldment. A scan for reflectors that are oriented parallel to the surface and a scan for reflectors that are oriented transverse to the surface. In both cases, the scanning should be performed at a gain setting at least 2 times the reference level sensitivity established during calibration. Supplemental angle beam examination, automated UT can also be done. So volumetric inspection of weld may be performed by using one of the 4 automatic weld inspection techniques: pulse echo raster scanning. The technique inspects with 0-degree compression and 2 angle beam transducer interrogating weld from either side simultaneously. The compression transducer examines for corrosion or laminar defects in a base metal, and the angle beam transducer scan the volume of the weld metal. Pulse zone inspection can also be done. So zone inspection is a line scan technique. The technique can use area of the transducer on either side of the weld with transducer angle and transit the time gates to ensure that the complete weld or volume of the weld is covered. So these are some advanced techniques that are used. In most cases, these will not be generally used, but it depends on what kind of operation we are working with. Next is the most commonly used are TOFD and phased array. These are one of the most established techniques which are considered to be advanced UT techniques. Manual UT will only tell you about the discontinuity, and other things are guesswork or it are subjected to calculations. But TOFD is going to be one of the best techniques to identify cracks or the length of the cracks, generally give you a B scan image. Phased array is generally going to give you a scan image and it will scan the entire section of the weldment. TOFD, this line scan technique used in pitch catch mode. The multi-mode transducers are used to obtain the maximum volume inspection of a weld region. More than one set of transducer may be used for complete volumetric examination. Phased array inspection, this technique utilizes the array of transducer element to produce steering of the ultrasonic beam axis or focusing of ultrasonic beam over a specified range. This allows the user the ability to inspect certain portion of the weld zone of a component tested using many different beam angles. Discontinuity evaluation and sizing. So generally we are going to use DAC to identify the discontinuity, but sizing technique can also be done by 6 dB drop and 20 dB drop technique. 6 dB drop is generally used for identifying length of the defects, and 20 dB drop is generally used to identify the length of smaller discontinuities such as porosity or slag inclusion. So one of the commonly used sizing technique is called as intensity drop or 6 dB drop technique. The sizing technique used for beam spread of transducer is quickly estimate the axial length of the discontinuities. ID creeping wave method, this can also be used. The ID creeping wave method used the effects of multiple sound transfer modes such as longitudinal and shear modes to a qualitative size flaws. The method is used for global location of the flaws in bottom 1/3, middle 1/3 and top 1/3 regions of the weld. 3 distinct waves are presented with the ID creeping wave method. High angle refracted longitudinal wave approximately 70 degree, direct 30 degree shear wave which mode converts to 70 degree refracted longitudinal wave, and indirect shear wave can also be used. So these are generally 3 would be used for inside creeping wave method. Not generally used, these are very typical methods, but this being a recommended practice, it will tell you about everything. Tip diffraction method can also be used. High angle altitude method can also be used. Bimodal method can also be used for identifying the size of the discontinuity. Phased array methods where you are using phased array systems can also be used. Next is hardness testing. So hardness testing of the base metal, weld metal and the heat affected zone is often required to ensure that the welding process and any post-weld heat treatment has resulted in acceptable level relative hardness. This is generally true because what happens is whenever you are doing welding, so welding can be considered as mini casting, okay? So whenever you are doing welding, when the weld metal cools down or because of the heat applied during the welding process, the area around the weld, that is heat affected zone, can be subjected to increase in hardness, or the grain structure around the heat affected zone can become coarse, which can result in increasing hardness. This is generally true for medium carbon and high carbon steel or high alloy steel. So to curb this, we generally would do preheat and post-weld heat treatment. So after post-weld heat treatment, is the hardness gone down or not? This can be identified by hardness testing. So the heat affected zone can be difficult to locate and often assumed for testing purposes to be just adjacent to the toe of the weld. The hardness testing for PQR is easier because the coupon is cross-sectioned and edged to identify the weld and the weld interface and the heat affected zone. API 582 details the hardness requirement for PQR and production welds. Hardness testing of repair welds. On-site hardness testing may be required on pressure retaining welds after post-weld heat treatment in accordance with API 582 and NACE SP 0472. Using API RP 582 as a reference, the heat affected zone hardness reading may include location as close as possible, approximately 0.2 mm from the weld interface. The surface should be polished and should not exceed 0.4 micrometer maximum, the roughness. After the surface has been polished, it should be etched to identify the weld metal, weld interface and the heat affected zone. This is the examination that is given. An example of hardness, how hardness measurement may be conducted, is shown in figure 57. 5 impression in the area approximately 1 inches should constitute a test because the field hardness measurement tend to have greater variability. The additional tests such as field metallography can be conducted to determine the excessive hardness of the microstructure that has been formed. So you will take multiple readings, and once you get multiple readings, you will understand that the hardness value is changing. And when you see, so let's imagine something like this. So you'll take hardness value here, you'll get some hardness. You'll take hardness value here, you'll get some other hardness. As you keep on going away from the weldment, your hardness value will keep on decreasing. At a point where hardness value goes constant, so that is the extent of your heat affected zone. Next is leak testing. So when hydrostatic or pneumatic test is required by the code, the inspector should adopt the code specification requirement relevant to the vessel or piping, API 510, 570, 574, ASME P313, ASME PCC to provide the guidance on the application of the pressure test. Typically the pressure test should hold at least 30 minutes or whatever is referenced by the code section. Leak testing of the welded tube to tube sheet joint may be specified for specific applications that are sensitive to small tube to tube sheet joint leaks. Helium leak testing is especially effective for tube to tube sheet joints when highly sensitive LT is required. Typically, the area under the test is found to be acceptable if there is no continuous bubble formation observed. If the unit under pressure is found to have a leakage, it should be depressurized and the leak shall be repaired and the test shall be repeated. Generally, leak testing will tell you about the leaks, but there are various kinds of leak testing that can be done based on the sensitivity required. You can do bubble leak test, you can do vacuum box test, you can do halogen tracer gas test, and you can also do helium mass spectrometer test. Bubble leak test has the lowest sensitivity, whereas the helium mass spectrometer leak detector would have the highest sensitivity. A wide variety of viscous fluids and methods can be used dependent on the desired result. Considerations for system design limitations may prevent the use of water. Drying hydrostatic head and support limitation should be addressed before the water is used. The required sensitivity of the results may also require a more sensitive leak test medium and methods. Okay. So this was the non-destructive testing part, that was section 8 for API 577. We'll talk about how to do welding inspection in the later section, but this was the non-destructive testing requirement that was given in API 577. So in the next lecture, we'll go for welding inspection. Thank you.